So we now start with lecture 21, and essentially we have been talking about this incongruent benthic relationships in a binary system. Now we extend this understanding of this to another very famous phase diagram, which is called anorthite phosphorite quartz. This ternary phase diagram, anorthite phosphorite quartz, where this shows a peritectic relation. Phosphorite quartz shows a peritectic relation, but anorthite quartz and anorthite phosphorite, these show eutectic relationships. So anorthite phosphorite shows eutectic relationships, anorthite quartz shows eutectic relationships. So you have two eutectic relationships, and in one binary, which is the phosphorite quartz binary, we have a peritectic relation, as we have discussed in the last class. Again, I will ignore the high temperature parts of the diagram. It creates a little confusion. Not confusion, it just makes it more cumbersome to handle, but I think it's best for us to understand what's going on at the moment. We start with first a three-dimensional diagram of the anorthite phosphorite quartz phase diagram, and then we move over to a projection. So So this is how the phase diagram looks like in three dimensions. So this is phosphorite plus liquid, hence to tight, phosphorite, quartz. This is anorthite plus liquid. This is enstatite plus liquid. This is phosphorite plus liquid, and this is SiO2 plus liquid, and these are the isotherms. All phases are taken to be pure phases. All phases are taken to be pure phases. There are no solid solutions in this phase. So we have temperature of, I will make this broken also. So it's something like this. You have two valleys, two hills from either side, which forms a liquidous surface of phosphoride and silica. As you will know once more, that is 1890 degrees centigrades. This is 1713 degrees centigrades. This is 1553 degrees centigrades. This is 1543 degrees centigrade is the eutectic temperature here, temperature of eutectic, and the peritectic temperature here is 1557 degrees centigrade. So it's very high temperatures. So we have a hillside, another hillside, and a slightly elevated land, and the arrows are important here. The arrow goes like this here, it goes like this, then the arrows are here, and here you give two arrows. So here there are two arrows, and all of them are one arrow, indicating they are simply boundary curves. But here, for example, this is called, this one here is called a peritectic. This is called the peritectic line, and this is called the cotectic line. And this is the smallest point, this is the low temperature point is here, which is the terminal eutectic. So this is the essentials of the phase diagrams as you project it, as you see it on a three-dimensional view. And it's important that we project this onto the composition plane as always. And so the diagram now, once you project it on the composition plane, this is the diagram that we will be dealing with. So this is how the phase diagram works. And here what we do is we join it with a broken line, and on this it divides the triangle into two parts. One is anorthite, phosphorite, enstatite, and the other one is anorthite, enstatite, and SiO2. So these are the so these are the two sets of diagrams that are given here. Now, I'm not giving you the temperatures, I've already given it to you here, so you can simply project it. Temperature of melting of anorthite 1553 degrees centigrade, phosphorite 1890 degrees centigrade, silicon 1713 degrees centigrade. This one here, I forgot to give it here. I will give it there so that you can take it out from there. This is 13. This temperature, so we are not giving you 1270 degrees centigrade. This is 1220 degrees centigrade. The eutectic is 1368 degrees centigrade, and this is 1350 degrees centigrade. 1350 degrees centigrade. So this eutectic is 1350, which is the anorthite phosphorite eutectic. The anorthite silica eutectic is 1368. The peritectic point changes from 1557 to 1270 degrees centigrade here. So it's like inclined towards lower temperature, so the direction of movement is always there. And 1270 here to 1220, slightly dip. So this surface is essentially dipping this way and this way. So that is what it is. It is this way and this way. So it's tilted on this side, this surface. So this surface is like this, and this surface is like that. It dips this way as well as on the right side. You can see from the temperature distributions. And this one is 1543 degrees centigrade. This is 122 degrees centigrade. I'm not giving you this temperature, but then you can just put them back onto this diagram and check it out. Now there is something important to tell you here at the moment, that this division line is a very crucial line. It's the same as in the phosphorite anorthite. You see, it starts from the enstatite plotting position and joins it to anorthite to a straight line, dividing the triangle into two parts. On this part, if you have liquid compositions, they will crystallize anorthite, phosphorite, enstatite, and those that plot on this part will crystallize anorthite, enstatite, SiO2. Now you must understand the following logic, and this is very important. If you have to, on this diagram, on this side of the triangle, which is anorthite, phosphorite, enstatite, this peritectic point here, this point, this has anorthite, phosphorite, phosphorite, and enstatite along with the liquid. So this is the last liquid that is in equilibrium with anorthite, phosphorite, and enstatite. Have you understood? That liquid, anorthite, phosphorite, enstatite. Because if the liquid, the liquid movement is this direction, so ultimately it will crystallize here. Any liquid leaving this peritectic point here and going on to this will end up in the eutectic. Once you are in the eutectic, and this point you see here, this point, here, you will have enstatite, silica, and anorthite in equilibrium with the liquid. Once again, this triangle on this side has anorthite, enstatite, and SiO2. Anorthite, enstatite, and SiO2. So essentially you will end up in the eutectic. But if you are in this part of the triangle, anorthite, phosphorite, enstatite, on the right side of the triangle, on the left side of the triangle, then your liquid should not cross over from peritectic towards eutectic. You cannot allow that liquid to cross over. So that's a very important part of understanding the diagram. So, like, if I have a point here, say for example, it's very crucial. I will not answer the whole thing. You should find out, but I will tell you how to reconstruct it. If you have a point here, and if you have a point here, this point will give you anorthite phosphorite enstatite. This point here will give you anorthite enstatite silica. Or for example, if you take this point and this point, the one on the left will give you anorthite phosphorite enstatite, and one on the right gives you enstatite, anorthite enstatite and silica. And there is a reason why this is so. It's a very crucial why this is so. And while I will teach the general cases, I will leave this discussion for you to understand why this happens. And the truth of it lies in the phosphorite-enstatite relationships that I taught you. Beyond the line, remember, beyond the enstatite line, on either side, even if there is a small difference in composition, it will in that binary diagram, if you have points to the left of the diagram towards a phosphorite end, you will get phosphorite enstatite. If you get it on the line, you get only enstatite. And if you shift right of the line, you get enstatite plus quartz. The same logic applies here also. But I will not tell you specific to this diagram. I will not tell you specific to this diagram why this happens. It is for you to find out. What I will tell you is general ideas about why it should happen, and with your background you should be able to find out why even so small differences in composition in the melt, initial melt or initial rock for melting, why do they produce so diverse type of assemblages? Right. So we start with the first assemblage, and I think you all know it, but I will still, best is I will try, and we all come, as I told you, we all come from different colleges and different courses, and I don't know, and it's very difficult for me to monitor how everyone is processing. So it's better to keep you at the same plane as far as I am concerned. And so I will go ahead with what I'm doing. But one thing is for sure, when I have asked at the end of the class, even to people who come from colleges which have good courses, etc., and people who have come from colleges, where it's not as stringent as it, and both have said that both of them had been greatly benefited from the lectures. So I think both of you, that means those who have come from good schools and those who have come from not so good schools, and I think all of you will find something very interesting. Right. Now let's say I am starting, mark my words very carefully. If I say I am starting from a composition here, a liquid L0. This is my L0 composition. I am deliberately taking this point very close to this broken line. I've taken it deliberately, not by choice, not by accident, by choice. Along this line, you can understand, along this line, for melts along this line, you will only get anorthite and enstatite. You will not get either phosphorite or silica. You must remember this. In this diagram, if you have melt compositions along this line, that's why I put L0 very close to this point, you will only have anorthite and enstatite. You will not have phosphorite, or you will not have quartz in the final rock. I'm not talking of the initial crystallization. Now, the final assemblage will consist only of an orthite and an instatite, and not fosterite or silica as the last equilibrium assemblage. And we are talking of equilibrium crystallization. So, as with all phase diagrams that we have started for the ternary and the binary, when you have your point of the magma which is on the fosterite field, and it plots directly intersects the fosterite solidus, so your point is somewhere here, or very close to this point somewhere here. Then you plot from the fosterite end, you start from this fosterite end, and you extend the line a little bit, and this is L1 and this is S1. Now, I don't have to go into details as to what I did, but just quickly, if this is P and this is Q, if this is P and this is Q, P by P plus Q is equal to the fraction of L1 of melt, L1. P by P plus Q is the fraction of the melt, and Q by P plus Q is the fraction of solid. And the composition of solid is S1. This we have repeated several times. What happens now is, as we crystallize further, remember we are crystallizing. As we crystallize further, the liquid composition moves straight away onto this position, and let's say this is L2. Now, when you are here, the position is S2. I have plotted L2 almost on the reaction line. So, if I plot along the reaction line, you must understand what is an equilibrium. Fosterite, instatite and liquid. Along the reaction line. Along the reaction line, what will happen? Fosterite 70 plus silicate 30 will react to give you instatite along this line, all along this line. That proportion is not going to change. Fosterite 70, silica 30 would react to produce instatite. So when I write L2 here, just on the line, I mean not on the line, just to the side of it, you still have S1 and S2. Right? Now you see the temperature, and ultimately here you will reach the reaction boundary curve. So as you reach the reaction or the peritectic line, if you reach the peritectic line, you can't have only fosterite and silica. You cannot have it. You will have to have fosterite, instatite and melt. And instatite has to be produced through a reaction between fosterite and silica in the ratio 70:30. So, and once you do it, then the liquid has to move in this direction. Let this be L3. Let this be L3. Now you see what happens. The moment you say that your liquid is L3 and this is your initial liquid composition, then now I have to join this L3S3, L3S3, and this should be L0. Have you understood? S3L3 and L3S3 and melt in equilibrium. Then if you are here, then you don't have only fosterite, you have fosterite, instatite and melt. So what is the proportion of fosterite is to melt? What is the proportion of solid is to melt? Very simple. P on this line and Q. P and Q. P by P plus Q on this line, and it will give you the fraction of melt. 1 minus that is the fraction of solid. The fraction of solid, or the proportion of the solid. So you have a magma, you have melt and the solid. So if you take L3, or for example, I will just write it is better, L0S3 divided by L3S3 is equal to P by Q, P by PQ plus P, and this will be equal to fraction of melt. Once again, L0S3 divided by L3S3, that means P divided by P plus Q. This should give you the fraction of the melt. 1 minus that is the fraction of the solid. Now, so your solid composition is now moving in this direction. Why? Because your melt composition is moving along the peritectic line. That means the proportion of phosphorite, remember, this is the length that you should be considering now. This length, phosphorite and statite proportion. You can find out this length. You see the amount of N-statite is increasing and the amount of phosphorite previously 30 to 0, that means 100%, which was S1, and now you have S3. So the proportion of phosphorite is decreasing. The proportion of N-statite is increasing because of the reaction between phosphorite and melt, silica, in the proportion of 70s to 30. And this will continue till your melt reaches L4. Reaches L4. So what will happen at L4? This will what will happen at L4. So this one here is now S4. So now your S4, L0, L4. This is your line, in which again L0 S4 divided by L4 S4 is the fraction of the melt. So what is in equilibrium now? In equilibrium now is you have a melt. What is its proportion? This is its proportion. P by P plus Q is its proportion. Right? So I know the proportion of melt and I know the proportion of solid. And the melt is in equilibrium with phosphorite and N-statite. So, and what is the proportion of phosphorite? I can see this divided by this is the proportion of N-statite. This divided by the whole, that's the proportion of N-statite. And the rest of it is the proportion of phosphorite. So long phosphorite, N-statite and melt are in equilibrium, the melt cannot leave this point. Yes or no? As long as phosphorite, N-statite and liquid are in equilibrium, the melt cannot leave L4. Because if it moves this way, it should have anorthite and statite in equilibrium only. No phosphorite. But you have phosphorite. So the liquid cannot move, becomes almost immobile at L4. But at the same time, phosphorite and melt are reacting to produce N-statite. And here when you reach L4, anorthite also starts to precipitate. So there are two things. At this L4, the melt composition will become immobile. Why? Because here, phosphorite and N-statite are in equilibrium here. If the melt moves here, there is no more phosphorite on So forsterite should not be in the rock at all. So the melt cannot leave this place. At the same time, anorthite has to crystallize. So first, the liquid cannot leave L4. Second point, the proportion of forsterite should continue to decrease and enstatite should continue to increase. Okay? At the same time, anorthite has to co-precipitate now. So the only way this can be done is this point S4 here, which was lost in equilibrium with L4, has to move up. Why? Because anorthite has to be produced. Have you understood? So let's say you have S5. So you have S5. L5 will continue to be. Okay? Now, I draw a line at S5. Okay? And this is the line to anorthite 30. So you see here what has happened? This amount of anorthite is now a part of S5. This much amount is a part of anorthite is a part of S5. And you can see here, from this point to this point, this is closer to 30. In anorthite 30. This has moved towards the right. So if it has moved towards the right, then enstatite has increased, proportion of enstatite has increased. Forsterite has decreased. It is expected because you're still in contact with the boundary reaction curve, and therefore forsterite is continuously being precipitated into, reacted out of enstatite. And this S5 therefore is a very good example where you have started to precipitate anorthite in your rock. More of more of forsterite that you have reacts to produce enstatite. So the proportion of enstatite is gradually increasing. And you see here, this P now, you see this L0S5 divided by L5S5. L0S5 divided by S5L5. Now you see the proportion of melt is also decreasing. So the proportion of melt is decreasing. That means the proportion of solid is increasing. If the proportion of solid is increasing, the forsterite by enstatite ratio is increasing. Enstatite by forsterite ratio is increasing, and proportion of anorthite is increasing. And all the while, forsterite, enstatite, anorthite and liquid continue to be in equilibrium. Continue to be in equilibrium. Be very careful of what I am saying. So when will the crystallization stop? When L0S5 will move, S5 will move to L0. Then Q will be equal to 0. So the fraction of melt will be equal to 0. And then the solid will have this composition. This is S6 or this is S6. Have you understood? This is exit, this is the amount of anorthite. And you can see here this line has moved into this position. Now this is a very, very critical position that you have reached. I will not tell more. This is a very critical position you have reached. If you have more than 100, if you have 100% enstatite, remember, if in the rock there is no more forsterite, all forsterite is consumed, then what will happen? The liquid has to move into this field where forsterite, enstatite, anorthite and silica becomes equilibrium. So there will be a point in this line somewhere. You know, I was making those 2 points very close by. Somewhere there, the proportion, you see, you have to get the proportion from an height 30. The moment you cross over, if N-statite, if phosphoride becomes 0, then it's completely different. The liquid will force to move into the eutectic. Will be forced to leave the peritectic because it doesn't. The system does not have any more phosphoride. It has anorthite, N-statite, and silica. So that's when it will move away. So this line and the position of AN30, this incongruent melting, the moment all phosphorite is consumed, you will have N-statite, silica, anorthite. The liquid moves away from this point and will move in the direction of the eutectic. Have you understood? So, and this will continue. We will do that. I have some time. We will do that and I will show it to you. But I won't tell you more about this. I have given you a very critical advice that this line and the proportion of phosphorite and anorthite is very crucial. The moment phosphorite is exhausted, first you had phosphorite, N-statite, anorthite in equilibrium with the melt. If phosphorite is completely consumed, then you have N-statite, anorthite, and melt. The melt cannot be here anymore. It has to move in this direction. Has to move. And once the liquid moves away, it will end up at the eutectic. It will end up at the eutectic. Once the liquid moves from here, it will end up at the eutectic. No escaping. You cannot escape. You can't stop the liquid anymore. So that is why you have to be this line is very critical. These are not drawn for doing any jumla. These are drawn at great significance. And the position of the incongruently produced mineral is very, very crucial. Okay. Now I will talk about crystallization from another point, and then we will stop over, and then we will stop. It's important to see different variations. I will take a little time to clean this up, clean the mess. Right. Now we let's take a point. I am discussing the second step. I will go a little quicker because I think I have some time, but I think I will go a little quick. Be with me. I am taking a point here. I I am taking a point here. Look at the position of the point. I am outside this. I have done it deliberately. Last time, I took a point on this side of the line. Now, I am taking a point this side. So now, but the point plots on the forsterite liquidus field. So, the first thing is, this is L0, this is S1, and this is clearly L1. With, and you know, P by P plus Q. I will write it here so that, you know, we always maintain this P by P plus Q. This is P by P plus Q, you know, the fraction of the melt. Here, my point I have drawn here till now is L1, which is on the left hand side of this reaction boundary. That means I am still on the forsterite phase field. So forsterite will continue to precipitate, and I know the composition of forsterite will be L0. This is L1 point, and I know all the temperatures, isotherms on which it is. I know all the parameters. Now I reach this point. I reach this point. Have you understood? And obviously, if I reach this point, then I move a little bit here, and I am on L2. Have you understood? So at L2, what will I do? I will do this. Yes or no? I will do this, L2. Yes or no? So what has happened? At L1, after that I reached the peritectic line. At the peritectic line, what happened? Whatever forsterite was there started to react with the melt to produce enstatite. Along this line, forsterite, enstatite and liquid are in equilibrium. No anorthite. Forsterite, enstatite and liquid. Forsterite plus liquid giving enstatite, because this is the peritectic line, the reaction boundary. So forsterite 70 reacting with silica 30 to produce enstatite, 100 enstatite. So what will happen? There is more enstatite that will be added to it. So what will happen now? After some time, somewhere, after some time, as we go up on this, you see, that is where you will stop. You will reach. Somewhere here you will reach. Where? Let's say this is L3 and this is S3. What is happening? At S3, look here, at S3, what is happening? At L3, S3, what is happening? You have now maybe one crystal of olivine still left. You have still, but because it shows 100% anorthite, 100% enstatite, there is no forsterite anymore, 100% enstatite in your solid, which is S3. It is in equilibrium with the melt. Olivine crystal, maybe the last grain of olivine crystal is being exhausted. So what will happen? If you are here, then forsterite is no more there. So the melt will not be here. The melt cannot be on the peritectic line for the simple reason there is no forsterite. There is no forsterite. So the liquid has to go into a field. So the system has to go into a field where you have enstatite plus liquid. Enstatite plus liquid. That is what it will do. Where is enstatite plus liquid? This is the only field where there is enstatite plus liquid. So the melt has to move. Do you understand? The melt has to move into the, as you have got the enstatite here, it should move into the enstatite field. It has to precipitate now only enstatite. You had enstatite previously through reaction from forsterite, from peritectic reaction from forsterite. That enstatite is there, but now you have enstatite plus liquid. So you can't be on the peritectic line, you have to be in the enstatite plus liquid field. That means you have to directly precipitate enstatite in your rock from the melt, but nothing else. Nothing else. So what will happen? From forsterite plus liquid you started. After that, the forsterite reacts with the liquid to produce enstatite, changing the composition of the solid along this line. And then finally the liquid was moving along this. And when composition plagioclase came here, you joined it, and then you had enstatite plus liquid. Once you had enstatite plus liquid, say for example, and then finally if you follow this on the line, you will reach this point. Anodite and enstatite. Because this is the phase field of anodite plus enstatite. Now I will ask you a question and I will not answer this question. You have to find out. So if now I have, okay, I will give you a hint. I think you might have figured out. If you have now anodite and enstatite, then what will happen? If you reach here and you start precipitating anodite to enstatite, then how will you find out what is the proportion of enstatite and anodite? Very simple. As it moves along this, join L0. I will do it with the red line. Join L0. To this line, anodite enstatite. Do you understand? This line, anodite enstatite, if it has moved to say L4, then this is your S4. If this is your S4, then you see in this line, anodite, S4, and enstatite. And if you do this A and this is B, then A divided by A plus B, A divided by A plus B is the proportion of enstatite. Is the proportion of enstatite. Have you understood? So, what you have to do now, you have to take this line on this side and join it with L0 and extend it to this anodite enstatite binary. Where S4 intersects it, you will get the proportion of enstatite and anodite. And you're precipitating enstatite and anodite. Precipitating enstatite and anodite. And this will go on till you reach this point L5, and for this you can see this is S5. Do you see? It is this L0 and this is S5. So when it reaches here, then you have S5. That means your proportion of anodite has increased. Proportion of anodite has increased. And when you do this, now your liquid is become immobile at the eutectic. And therefore subsequent solid will move towards L0 so that P divided by P plus Q will become equal to 0. Have you understood? So that at this point S4 as with more crystallization S4, this S5 will move towards L0. Now I will leave this today's class with a question. How will you find out the proportion of anodite is to enstatite is to quartz or silica, this ratio in the solid for crystallization at the eutectic. How will you find out? At this point, what will you crystallize? Previously, you started crystallizing phosphorite, then the phosphorite got exhausted, then you started crystallizing only enstatite, then enstatite at anorthite, then enstatite, anorthite, and silica. And the solid starts to move in this direction and reach L0. How will you find out what is the proportion of anorthite, enstatite, and silica in the solid and in the liquid? Liquid you can find out for crystallization at the temperature we take it. How will you find out? I think I have taught enough so that you can find a way to find it, or read the book by Winter, or you can read the book by Philpotts and Ague, and you can try and find out the answer. Okay? If not, you let me know over the Google Classroom, and maybe if it's possible, I will take a class. But I expect you to learn it yourself. Thank you.